So let's get started. And what do we have first? Oh yeah, I need to tell you what I'm going to do. Types of functional groups, that's what we're going to cover. So by the end of this, I'd like you to be able to recognise different functional groups within drug molecules and use correct terminology referring to these functional groups. So no getting confused between an amine and an amide, and then we'll all be okay. So, right, let's start with carbon. Now, carbons, if you've got carbons joined to other carbons, and they are joined by single bonds, we call these alkanes. So here is an example where we have drawn out all of the bonds, all of the atoms, and as you will see as we go through this screencast, I've got all of the bonds and atoms example, simplified version, and some other examples as we see fit. So you can see that actually drawing all of this out is rather cumbersome. This is actually a bit easier, and if all of these R groups were hydrogen, we would just draw a line. And us chemists know that that means a carbon is there, that means a carbon is there. If we want another one, we just draw another line here. If we want another one here. We'll see that in a minute. I'll show you the different lengths of carbon chain you can get. So, if we took this molecule and we wanted to name it, we'd call this ethane. It's got 2 carbons in it, so we call that ethane. It was only ethane if it's isolated on its own. If it has something attached to it, like here, we've got a bromine attached to this ethane group, it then becomes an ethyl group. So we call it ethane when it's isolated on its own, and then the terminology changed to ethyl if it's attached to something. So here we've got it attached to a bromine, then becomes an ethyl group. So this is something that is common to quite a lot of different functional groups. It'll end in "-ile" usually for quite a lot of functional groups. So let's have a look at some different types of alkanes. So if we've got 1 carbon, we call it a methyl group. If you hear some of these American videos, I sometimes call it a methyl group, but it's the same thing. 2 carbons is an ethyl, so that's what we saw in the previous slide. 3 is propyl, 4 butyl, 5 pentyl, 6 hexyl, 7 heptyl, and 8 octyl. I could go on, but I think you get the general gist of it. In addition to these, sometimes you'll see different versions. So propyl, you can have all of the carbons just attached to each other in a line, or you can have your R group attached to the middle carbon. So here we've got it on the terminal carbon, but here we've got it on one of the middle ones. So this is actually, instead of being propyl, we will call this isopropyl. Now I've used this as an example here. It's worthy of remembering because quite a lot of drug molecules will have this functionality in it, and it's one that's worth remembering. Similarly, tertiary butyl, it's basically a butyl, except instead of having all of your carbons in a line, you've got them like in a little bunch like this. I like to think it looks a bit like a hand. A gammy hand, I'll give you that. But these are tertiary butyl groups. You'll see those a lot within the next year or so, in particular in the 2nd year, when you'll learn more about protecting groups with Professor Ganasan. He'll be showing you protecting groups that have tertiary butyls on. So keep an eye out for those. As well as alkanes or alkyl groups that are in a chain, you can sometimes find that you'll find them in cyclic sort of formations. So here, instead of this being hexane, we've got cyclohexane, which means it's in a circle, or it's cyclic. Here we've got cyclopentane. Now, if we were to bang on a R group on this, we go from it being cyclohexane to a cyclohexyl group. See, same thing. Here we've got cyclohexane, and if you put an R group on it, it turns it to a cyclohexyl group. So, bit of a pattern going on there. So, what have we got next? Have a drink of my tea while I'm going on here, otherwise I'll get a bit hoarse. Okay, so we've had our alkanes, and they're with single carbon to single carbons, so carbon-carbon single bonds. If we have double bonds between the carbons, they are called alkenes. So here's our cumbersome one where we've drawn out all of the bonds and all of the atoms, and this is the simplified version here. Now with double bonds we can get two different types. We can get cis double bonds, and that's when the R groups are kind of on the same side. And we can get trans ones, and they're like kind of across from each other on opposite sides. Now the cis double bonds are also termed as Z. Sometimes you'll see that they're called Z double bonds. And trans ones you'll sometimes see drawn up as an E double bond. Now, the way I remember this is like, basically I kind of expect the trans one to be called a Z, because that looks a bit like a Z. Well, obviously that is a Z, sorry. But that also looks like a bit like a Z, so they're like opposite each other. And the cis one, you could say, oh, that looks like a C, that looks like a C, that almost looks like a C, so that's cis. But basically it's the other way round. I know there's a reason for this, but it doesn't really, doesn't really make sense in my head sometimes. But if you just remember the alkenes, you expect the cis to be the E and the trans to be the Z, but it is the other way round. So cis is Z and trans is E. I'm sure it's quite easy enough to remember. You probably already got it sorted in your head. So, got done our alkanes, and that's single bond, single bond carbons. Done our alkenes, and those are the double bonds. If you have a really greedy carbon and it has 3 bonds attached to it, we call that an alkyne. So here's our triple bonded carbon. Here they are. And if we want to make it simpler, that's what they look like. So this R group can be an H. Could be an H here. But as a chemist, we know that that's a carbon there, and that's a carbon there. We don't need to draw one in. We know it's there. If we don't say what it is, it's a carbon. And if there's nothing attached to it, it's a hydrogen. So basically, if there's nothing there, like here, that's a hydrogen. And if there's nothing at this point here, that's a carbon. So just makes things simple. Because when you're drawing out large molecules, you don't want all of this stuff in the way. It looks really cumbersome and takes up a lot of space. Okay, so moving on. Aromatic carbons. Now you'll learn a bit more about aromaticity soon enough. And you've probably already encountered benzene. But aromatic carbons have double bonds in them. But we term them in different ways. So this is benzene. But if we attached an R group to it, if we bang on our R group here, we call that a phenyl. We could call it a phenyl group or a phenyl ring. Either's okay. Some people call it an arene ring. Dr. McDermott likes calling it an arene ring. So either's fine. Now I want to draw your attention to the differences between cyclohexane and benzene. Cyclohexane is an alkane. It has no double bonds. It is not flat. It has one of those little wiggly structures that you'll learn about more in detail with Dr. McDermott. This benzene, flat. Flat, aromatic, loves to stack on top of itself. If you look at 2 drug molecules, when you draw them out like this, they look pretty similar in terms of size, structure, etc. But they are completely different. So make sure you don't get these two confused. So this is an alkane and this is an aromatic ring. This is flat and this is actually, you can get different conformations, chair and boat. But you'll learn more about that detail later on. But these are different. Do not get them confused. Cyclohexane, benzene. So, cyclohexane, benzene. And Dr. Matthews won't get upset with me for not telling you. So, you heard it here. Benzene, cyclohexane, done. Right. Now, if benzene's got stuff attached to it, it can have stuff like in the ring here, like we call this a heteroatom, this nitrogen in here. Or if it's got stuff attached to it, we'll call it an aryl ring. So if I had another group off here, like a chloro group, we could say this is an aryl ring. So here we've got a specific example that I want you to know is pyridine. You might have heard of it before. If you haven't, then it's a very pleasant molecule that makes people infertile, but we won't hold it against it. If you put on an R group here, we go from calling it pyridine to a pyridyl group. So that's a very specific example. I'd be happy enough for you to call that an aryl group, but pyridyl is the very specific example. Now, in addition to pyridine, there's a few other molecules I'd like to introduce you to. This is phenol. It is an aromatic amine. No, it is not an aromatic amine. That is aniline. I get confused. This is an aromatic alcohol. But you can call this group phenol. Even if it had something attached to it here, you could still call that phenol. I'd be happy with that. You could call it aryl. That's also okay. And if you change from having alcohol to an amine, we call this an aniline group. So this is aniline, and you could say that's an aniline group as well. Another common one that you might encounter is toluene. Toluene was pretty much used to replace benzene, which is a nasty, toxic compound. Toluene's got similar properties to benzene, but is less toxic. And you might see that in your aromatic chemistry with Dr. Howell. Imidazole. I think this is important because it is in lots of drug molecules. It's also part of histamine, and it's kind of important in that. Also, it's involved in amino acids, and also therefore peptides and proteins. So because of this, it's actually involved in quite a lot of enzyme catalytic sites. So imidazole, remember that, it's a really useful molecule, and you'll see it loads. So remember the structure, and then that'll be easy for you. Finally, I've put indole here because it is a so-called privileged scaffold. Now, privileged scaffold means that it is present in lots of molecules with biological activity. So you'll find this type of structure in lots of drug molecules and lots of molecules that are active in biology. And we call it privileged because lots of compounds have this structure, and we think that the actual structure of the indole imparts biological activity. So indole's another useful one. I think it's important for you to know. So moving on to different functional groups that are less focused on carbon, if we move on to the alkyl halides. Now, hopefully you're familiar with using X instead of a halogen or a halide. Here's what they look like if you draw out all of the atoms, and this is what it would look like if it was a bit simpler. And this is the bare bones of the functional group RX. So if you've got a fluorine, you would say this is a fluoro group here, or that the molecule's an alkyl fluoride. Similarly, chlorine, this is a chloro group, and we call this an alkyl chloride. Bromine, this is a bromo group, and then the whole thing's an alkyl bromide. And then finally, iodine, that atom here, this is an iodo group, and then the whole thing's an alkyl iodide. Notice how I've started to use a bit of colour here. Apparently this is the colour of fluorine gas. The colour of chlorine gas is green, bromine gas is brown, and iodine gas is purple. It's beautiful, isn't it? But colours make me happy, and maybe they'll keep you a bit interested. Oxygen is blue. Did you know that? No, I didn't really either until not long back. Apparently liquid oxygen has a blue tinge to it. So go look that up on Google Images. Okay, so when we think of oxygen, first functional group that comes to my mind is an alcohol group. That's when you have an oxygen attached to a hydrogen attached to whatever you want your R group here, an alkyl group. So this is what it looked like when you draw out all of the atoms. Here's the simplified version, and here is the bare bones. If you were to write out on one line, that's what you would write. So if your hydroxyl group, or your OH group, is attached to your carbon, and that carbon has one thing attached to it, we call that a primary alcohol. So look, OH, hydroxyl group, OH, alcohol group, attached to carbon, which is attached to one alcohol group. Now, if we were to have two things attached to this carbon, here, so here's your OH, here's your carbon it's attached to, that's attached to two other things, call that secondary alcohol. And if this OH is then attached to a carbon which has three things attached to it, call that a tertiary alcohol. So primary, 1, secondary, 2, tertiary, 3. So there's a bit of a pattern there. You'll see this again and again in terminology. We'll come back to that later. Here we have phenol again. I'll put it in here as well because it's an alcohol. I would call this an aromatic alcohol. We could also call it phenol, and you could say that this is a phenolic OH. That's okay. Excuse me. So if we then move on to greedy oxygens, this is oxygen, not content with having hydrogen attached to it, wants two R groups. So we call these ones ethers. This is an oxygen, got an R group here, got an R group here. This is the simplified version. Want to introduce you to two very common ones that you might come across. This is diethyl ether, or as us chemists like to call it, just ether. Same thing. I know that this is an ether, but we call this one ether because obviously that makes loads of sense. The reason we call this one ether is because that's the one we use the most. Was used as things to make people less worried about operations, kind of anaesthetics type things. You probably know more about that than me. I use it as a solvent in organic chemistry most of the time. And here's another one, cyclic ether. We call this tetrahydrofuran, or THF, and this is also used in lots of organic reactions. So I've just highlighted these two because I think they're important, and also because you're probably likely to encounter them. So when you see THF, that's what it actually is. So which is a cyclic ether. Now a special cyclic ether that I want you to be aware of is epoxides. So if you look here, you still have your carbons, and they're attached to the oxygen. So the oxygen is attached to kind of two R groups here essentially. But as you can see here, and I think it's the epoxides that show how cumbersome it is to actually draw out all of the atoms like this. This looks much cleaner and tidier. So here we've got both carbons, and then these R groups would be coming towards us, and these ones would be sort of facing away. So these are called epoxides. Now they're special because this system is actually very strained. So you'll know that an sp3 hybridized carbon would like to have a bond angle of 109.5 degrees. Now here we've got 60 degrees. So this is really strained. You've got to think about it like this is forced into this triangular shape. Now the reason epoxides are exciting and useful is because they're reactive, you can get something attack here and open up the ring. And because they're reactive, we use them to make drug molecules, but also they can be involved in functional groups within the drug molecule, and that might be important in its biological mode of action, or biological molecules like active biologicals or natural products can have epoxides in, and that's what's important. That's how they work, that's how they impart their mode of action, is by actually reacting these types of groups. So keep an eye out on these. They're really important, and you'll come across them again and again. Another one that I'd want to make you aware of is peroxides. You're probably familiar with the terminology peroxides in terms of using them as bleaching agents. Now a peroxide means that it's an oxygen that's attached to another oxygen, and both of these have the R groups on. So if you were to draw it out a bit like, the way that they're all being drawn out like this, but they're actually they would look a bit more bent like this, if you were to draw them out in real space. And if you want to write it out or type it up on one line, that's what it would look like. So this oxygen-oxygen bond's really weak, so you actually get cleavage here, and that's how you get radicals form, and that's the reason why peroxides bleach your hair, because they form radicals, and those then essentially start to destroy the colouring in your hair if you're bleaching it. Or if you're bleaching anything, in fact. I've bleached my towels, my husband is not very happy. But I pretend it wasn't me. I don't really know why, because it was me. Anyway, don't bleach your hair, and you don't bleach your towels either. Moving on. More greedy oxygen. So we've gone from the oxygen having single bonds, and now we're looking at oxygen with double bonds. So the first example, and the simplest one, is the aldehyde. So here we've got the R group attached to the carbon, and this has got two bonds to the oxygen, and then the other bond goes to the hydrogen. So we call this particular group here a carbonyl, and depending on what we have attached here, we call it different things. So if we've got a hydrogen attached here, call it an aldehyde. So here's the simplified version, and sometimes you'll see it with no hydrogen drawn at all. I always like to draw a hydrogen there, just to make sure that it is clear that I know it is an aldehyde, not that I've just forgotten to draw the rest of the molecule. Bear that in mind. Totally up to you. I prefer to draw the hydrogen there, just to make sure that I'm explicit. Look, there's no R group here. There is a hydrogen, and there is nothing else. Whereas if you kind of draw this, you kind of think, well, have I forgotten to draw something there? Is that what they've done? If you draw a hydrogen there, it's explicit, and you're being very clear. So, best to draw the hydrogen when it's aldehyde. Ketones are when a thing attached to the carbonyl is another R group. So that must be when there's an alkyl group. So if it's a chlorine or something else, it's a different functional group. But if it's another alkyl chain, it is a ketone. So you'll encounter quite a few of these in your studies. But one that I'd like you to be aware of is an alpha-beta unsaturated ketone. And these are special because they have a ketone group, so they're carbonyl. They have a single bond. And then the next carbon, it has a double bond attached to it here. So we've got an alkene here and a carbonyl here. And the reason these are important is because you can get things attack in here, like a nucleophile can attack in here, and then these electrons from this bond can travel up to this one here, and then these ones can go and localise onto the oxygen. You'll learn more about this in a few weeks' time. The reason we call this an alpha-beta unsaturated ketone, I'm sure you've got the ketone bit, is the ketone. The unsaturated bit is because you've got an unsaturation here, you've got an alkene here. And it's alpha and beta. Here's your carbonyl. The first carbon away from the carbonyl we call the alpha carbon. And then the next one is the beta carbon. The next one along would be the gamma carbon. So we are, we're not counting, but we are going through the Greek alphabet. So it would be alpha, beta, gamma, etc., etc. So this is the alpha carbon, this is the beta carbon. So therefore, this is the alpha-beta unsaturated ketone. So these are pretty sneaky. You'll find them quite a lot of different places. But they are special because we can say that this is in conjugation with the carbonyl. So this alkene is in conjugation with the carbonyl, and that affects its reactivity. So it's quite important. Right, moving on. Aldehydes and ketones can react in quite a few different ways. And the first way that the first intermediate that I'd like to introduce you to is a hemiacetal. And this is a derivative of an aldehyde. So imagine here is your R group, here is our carbon. If you imagine that had a double bond there, and there's your hydrogen. This is an intermediate on the way to an acetal group. So the hemiacetals have a hydroxyl group, so it's an alcohol, and then an OR, so an ether group. Whereas an acetal has two oxygens attached to the same carbon. So the definition of an acetal is a carbon with 2 oxygens attached to it, essentially. So we get, when we call these, when we name these compounds, we just call them acetals if they have OR on in each case, but it would be hemiacetal if there's only one OR and the other one's an OH. We have similar compounds, so if you had an R group here instead of an H, so if you started off with a ketone instead of an aldehyde, this would be a ketal. So this is ketal. I've drawn this out as a hemiketal, but actually that would only be a hemiketal if I had a hydrogen here, so I've made a bit of a mistake there. So if this was a hydrogen, that would be a hemiketal. This is actually a ketal here, even though I've written hemiketal there. Sorry. Anyway, this is a ketal, but I think you get the right, the correct impression. Hemiacetal, it's got a hydroxyl group. Acetal, just OR both times. Ketal would have an R group here instead of a hydrogen. And they're derivatives of aldehydes and ketones. You'll see those in a bit more detail with Dr. McDermott in a couple of weeks' time. And then again, when you do sugar chemistry with Dr. Hamilton in semester 2. Now, one of the things I want you to be aware of is, although this is an acetal, you'll kind of sometimes see this functional group here, which is very common, and you'll sometimes hear this called an acetal group as well, but it's spelt differently, or sometimes you'll hear people call it an acetyl group, so an acetal or an acetyl. But sometimes people will call this an acetal group, depending on how they pronounce things. So these are 2 completely different things. Obviously, this is a carbon. It's got 2 oxygens attached to the, to the same carbon. Here we've just got a ketone, and I'd call this a methyl ketone. It's got a CH3 attached to your carbonyl, so it's a ketone. The reason this is important is you'll see it used as a protecting group to mask the functionality of functional groups, and you'll learn about that in more detail later on in the course. And it's important because if you think of acetal or acetyl, this is actually part of the functionality in acetic acid. So this is where this functional group sort of gets its name. And if you've ever used the chemical acetone, that is simply this molecule except for another methyl group here. So it's basically kind of the mirror image of this here. So you'd have a methyl group here, methyl group here, acetone. So same principle for naming it. So I know it's confusing, and as chemists we love to use the same name for things. It's a very English thing to do. But this is an acetal and this is an acetyl group, so just be careful with that. Okay, moving on to acid derivatives. Probably encountered carboxylic acids before. This is when you have your carbonyl group attached to an OH group here. And here's a simplified version. This is what you'll see it drawn out like. You can have CO subscript to H or COOH, either's fine. You sometimes see people draw that out instead of drawing the same. That's okay. If instead of having an OH group here, you have OR groups, so you have another alkyl chain here, call that an ester. So again, here's the simplified version, and here's what it would look like if you drew it out on one line. Now, if you have a cyclic ester here, like here, see, you've still got the R group here, but the R group's actually attached around to this carbonyl group here. We call this a lactone. So it's a cyclic ester, and there's a very specific name, lactone. Now, if you just said this was an ester, that's absolutely fine. But if you said it was lactone, it would be even more specific. And lactone just means cyclic ester. And then finally, in terms of the oxygen acid derivatives, there are anhydrides, and these are I like to think of them a bit like special esters that are a bit more keen on reacting. So here you have your kind of, essentially you've got your carbonyl, you have it attached to an oxygen, so it's a bit like an ester. Then you have another carbonyl over here. Now that just makes it really easy for things to attack in here, like nucleophiles attack in here, and then this is good leaving group. So anhydrides are really cool. You wouldn't usually see these drawn out on one line or typed up, but that's how it would be typed up if you did. More acid derivatives. Now you see what I've done here, green, chlorine. These are acid chlorides. You sometimes hear them called acyl chlorides. That's also okay. So that's instead of having an R group here, you have a chlorine group here. So you have your carbonyl and then your chlorine. Here's what it looks like, a bit simpler. And if you draw it out in one line, that's what you'd write. And then instead of having chlorine, if you replaced it with a nitrogen, we call this an amide. And here's the simplified versions for you. Now amides, you can have primary, secondary and tertiary. So if the nitrogen has only one thing attached to it, remember the hydrogens don't count, one thing attached to it, primary. If it has two, so here you've got your carbonyl and then you've got the R group, that's a secondary amide. And if it's got three things attached to it, so here you've got one R group here, then you've got your other two, that's a tertiary amide. And a bit like your lactone with the ester, if you have a cyclic amide, you can call that a lactam. That an comes from amide. Now this would be a secondary lactam, because it's got two things attached to it. If you had a methyl or another alkyl group here, that would be a tertiary lactam. But amide's fine, lactam's fine as well. Now, if you've got a greedy amide, so you're not satisfied with having one nitrogen one side, you have to have another one the other side, this is called a urea group. You'll come across this more in the second year, but it's still important that you know that, sort of, to recognise it. So, now we've kind of started looking at nitrogen, we may as well kind of look at it in more detail. I always think of nitrogen to be orange, I don't know why, but in my head that's the colour that it is. So, passing that gem of useless, propagating colour love towards you. Amines. Amines are nitrogen that have got different R groups on. So, they're a bit like the nitrogen equivalent of ethers. That's the way I like to see them. So here's like if you draw it out in full, here's like the simplified version if you wanted to type up on one line. Now you can also get primary, secondary, tertiary amines. So primary amine is when you have just one R group attached to it. Secondary is when you have two R groups attached to it. Tertiary is when you have three R groups attached to it. And the cool thing about the amines is like they have a lone pair, so you can actually get four things attached to it, and we call that a quaternary. So the R groups could be it could be anything that's an alkyl chain, or it could be a proton. So call these quaternary nitrogens or quaternary salts, because if you have a positive charge, you can have a counter ion. So it will be a salt. So that's interesting. That's when the nitrogen's used its lone pair, acted as a base, acquired something else. So primary 1, secondary 2, tertiary 3, quaternary 4. See what they've done there. And finally, you've got these aromatic amine or aniline, which we met earlier in the aromaticity part. And one of the other examples I want you to kind of be aware of is an enamine. This is exciting. So if you have your amine here, you've got your alkene here, if these are separated by only a single carbon, a single bond, so if you've got your amine, single bond, alkene, you can call that an enamine. enamine, because the lone pair of the nitrogen can be in conjugation with this, and they're quite specific. So these are enamines. You could say this is an alkene and this is an amine, but if they have the potential to be in conjugation with each other, then you call it an enamine. It's quite cool. So if you have a nitrogen that is triple bonded to a carbon, you would call that a nitrile. Sometimes you'll see it called a cyano group. Either's fine. So if we don't draw the carbon out, that's what it looks like. And you probably come across a nitro group as well. So they're not amines, well, none of them are nitriles, but these are completely different functional groups. So you have your R group, and then there's the nitrogen that has oxygens either side, and these are kind of essentially delocalized. But it's easiest to draw it out as an NO2 group. You know exactly what you mean when you do that. Okay, so more nitrogens. If nitrogen's greedy and it wants more than one bond, we call that an imine. So here we've got carbon double bonded to a nitrogen. This is a bit like a carbonyl. See the similarity in structure? So if these are R groups, we can say, oh, it looks a bit like a ketone set with a nitrogen. We call these imines. Now, because I've drawn in the lone pair, because if you can have different isomers depending on where your R groups are. So if your R groups are here, that would be kind of like a cis one, and this would be like a trans one. Because the lone pair actually kind of almost acts as a group. So these are actually different isomers. So something to be aware of. So imines have different sort of similar cousins. Here are oxenes, so they have an oxygen on here. Hydrozones, so they have an extra kind of a minor group here. And a particularly useful one to remember is a guanidinium. So here you've got, here's your imine, and then you've got another nitrogen here and another nitrogen here. So, yeah, so it's a bit like a urea, except with more nitrogens. But guanidinium groups, again, you'll find them in amino acids, therefore proteins, and therefore in enzyme active sites and receptor binding pockets, but also in lots of drug molecules as well, so one to keep an eye on. Right, now sulphur. Next, I don't know why I think of sulphur to be green, because when I think, you learn about it at school, it's yellow, but that doesn't show up very well. Sulphur's special because you can get kind of different oxidation states, so it's not a bit like carbon has 4 bonds, and like nitrogen likes to have 3 bonds, and oxygen likes to have 2 bonds. Sulphur, it can have 2 bonds generally, or it can have 6, essentially, for what you're kind of thinking about in terms of your organic chemistry at this level. So here, sulphur with 2 bonds, we can have a thiol. This is a bit like an alcohol, except with the sulphur. That's the way I like to think about it. So, got that thiol here. Disulfide, this is a bit like a peroxide, except with the sulphur. So, you'll see these disulfides in disulfide bridges, which help help keep proteins together when they're folded. So yeah, these are similar to the peroxides, which are the equivalent with oxygens. Thioethers, again, these are like ethers, except with sulphur. So notice thiol, thi, indicates it's sulphur. So this is an alcohol, but except with sulphur, thiol. And this is an ether, except with the sulphur, so it's thioether. And then again, we saw urea before, and because we've replaced the oxygen with the sulphur, call this a thiourea. And yeah, so these are ones to kind of be aware of, but they're very similar. You'll see the cousins of these sulphur compounds with which contain oxygen. So they are very similar. So sulphur can have 6 bonds, so it can be really greedy. So there's a different oxidation state of sulphur when that's the case. So the simplest one that you can find is the sulfonic acid, and it looks like this. So your sulphur has 2 double bonds to the oxygen, so it's like 2 carbonyls almost, but except with the sulphur and with the acid, and that's what it looks like. Oh, I've missed out an oxygen there. That'd be SO3H. Made a mistake there again, voila, well done. So that's SO3H, sulfonic acid. If you replace the OH with the chlorine, we'll call that a sulfonyl chloride. So it's a bit like an acid and an acid chloride, except it's a sulfonyl group. So this is a sulfonyl group. So this is sulfonic acid, sulfonyl chloride, and then if you have your amino group here, that's a sulfonamide. So this is your acid, this is your acid chloride, and this is your amide. But if you have the sulfon group, then they become sulfonic acid, sulfonyl chloride, and sulfonamide. So you'll see these you'll see sulfonamides in lots of different drug molecules, and sulfonyl chlorides are what we use to make sulfonamides, so they're really important. Final thing that I want to make you aware of is phosphorus. So phosphorus, you'll see different types of compounds, but mainly involving phosphates. So you'll see the sugar phosphate backbone, DNA, and RNA, which you'll do with me in the second semester. But you'll see also phosphates as in ATP or adenosine triphosphate, and you'll see different derivatives like esters. So just bear in mind that generally stuff with phosphorus and lots of oxygen is going to be called phosphates. So just to remind you that the actual lecture will be about the top 25 drugs. So bring your top 25 cards to the lecture and be ready for a quiz. You'll be in teams, so I'm not going to have any limits on the size of team. You just kind of sort it out amongst yourselves. It's all for a bit of fun. And we'll go through some examples of functional groups to reinforce what I've just gone through in the screencast. So I shall leave you to it. Rewind, obviously, as and when or as much as you like. And I'll see you next week. Take care.